Welcome to the second day of our short online workshop. And so before we start with the first speaker, I just would like to remind everyone, perhaps those who were not here yesterday, that apart from this Zoom streaming, you can also watch, if you might have some technical issues, can watch this on the YouTube channel in live streaming. And if you're in Zoom, then you can also try to ask questions. Just use this Q&A button in the Zoom window and type your questions, and we will either ask directly then your question to the speakers or at the end of the talk. And obviously, like yesterday, there will also be later today question and answer sessions where then you can, perhaps in a bit more relaxed and longer way, ask questions about the topics. Okay. So this is, apart from this, we try to continue like yesterday. And we are very happy that we can now kind of make a change of gears after all these very theoretical talks yesterday. We now have an experimentalist telling us about what is happening in these systems. So our first speaker is Christoph Lienau from the University of Oldenburg in Germany. And he will tell us about the coherent ultrafast charge and energy transfer processes in nanostructures. Okay. So please, Christoph, the floor is yours.
Hi, good morning. It's a pleasure to talk to all of you. I hope you can hear me well. As Ralph said, it's interesting to speak here in front of this audience as an experimentalist. I apologize for this. Yeah, I will nevertheless try to basically give you a slightly different point of view from what you heard yesterday about some of the same topics. Specifically how charges move in nanostructures and what we understand about it or what we do not understand about it. We have a small group in Oldenburg. Oldenburg is somewhere in the north of Germany, close to Bremen. If you know Werder Bremen, they were once successful in soccer. Now they're doing not so well. And we have a nice city and a nice science center there, and we're trying with our group to basically understand ultrafast processes in nanostructured matter using space and time-resolved spectroscopy methods. So basically, we're using laboratory tools, ultrafast laser sources, high-resolution microscopes to probe as well as we can how charges and nuclei behave once they're confined to nanoscale geometries. And maybe one of the reasons why I'm here, at least I saw this some picture from this yesterday in Marco's talk, is that some time ago, like a decade ago almost, we asked some friends to tell us, actually some theory friends, to tell us about charge transfer. And we wanted to learn about charge transfer in a very simple molecule in principle. It's composed of three regions, a green one, a carotene, which does not matter so much. It's just there for stabilizing purposes. But here, this molecule has a donor, a porphyrin unit, and an acceptor, a fullerene unit. And upon light excitation, we were thinking, and others were thinking this as well, because we did not design this molecule, that light excitation basically generates an electron hole pair here in this porphyrin unit. And then this electron hole pair generation is followed by a charge transfer, an electron hopping from the porphyrin to the fullerene. And then we actually asked some very smart Italian theory friends to show us by computer means how this charge transfer works. And we were asking them this question because we had suspicions that usual pictures of electron transfer would actually hold in this molecule. And what they came up with was a movie. I hope you can see this here. It's a bit of a complicated one. Don't blame me for this. This has been done by Carlo Rozzi from Modena, yeah? But it's also an interesting one. What you see is the structure of the molecules. So the carotene, the porphyrin, and the C60, you see the light excitation, and you see that basically here light excitation creates negative in purple and positive excess charges. In total, the excitation is neutral here. And you can obviously see that this excitation is localized to the porphyrin region. Actually, the C60 does not contribute at all to the process. And we were a bit skeptical about this, of course, because we wanted to see a charge transfer process here. And our theoretician friends told us there is no charge transfer, at least not if this tiny linker region here was not flexible, because they basically, in this video that I show here, they locked the position of the atoms, which are free to move. In technical terms, they calculated the Ultrafast dynamics of these nuclei, but they locked the positions of the charges here. And as you can see, this locking of the nuclear positions here completely suppresses the charge transfer throughout the molecule. And they told us that if we would want to see charge transfer, we would have to unlock these positions here and to make the nuclei move in this linker region here, but also throughout the molecule. And in this case, if all nuclei are free to move, you can see that now light excitation also creates charge on the C60 here. And this was very surprising because we did not expect electron-nuclear coupling, something that already has been discussed yesterday, to play such a fundamental role for charge transfer processes. So we were puzzled about this, and we wanted to find out whether or not our theory friends were telling us the truth, because there was some suspicion in the community that time-dependent density functional theory, TDFT, would not work to describe charge transfer processes at all. This basically, this question, how does nuclear motion contribute to charge transfer processes, is what started a series of experiments in our group, and I will tell you a little bit about the progress of these experiments.
And Christoph, can I just interrupt for one quick question to this? In the last picture where there was charge transfer, it seemed that on the fullerene in the end, there's the same amount, or at least optically it looked the same amount of positive and negative charge. So is there no electron transfer towards the fullerene, or is there?
This is, I stopped the movie and I will come.
Now it's, okay, you stopped the movie, okay.
So now this is stopped 10 femtoseconds after excitation. And not sure how good your eyes are, but you can see that there's almost as much green as purple. Okay, so right now, the C60 is still charge neutral. The electron has not yet moved, or at least not completely. Now let's go on. And you see that now, after a while, it's almost purple. Okay. And the rest of the fate of the charge distribution, I will tell in the rest of the talk.
Okay, thank you very much.
Okay, good. Yeah, so here is where the story starts, essentially. So basically, we want to go through a sequence of processes, if I can, intramolecular charge transfer, intermolecular charge transfer in organic solar cells, conical intersection, some very new work that was accepted 2 days ago. And then I will talk about, go into the detail, are just short laser pulses, and I will tell you why. They look nice in the laboratory, so for those of you who are in the audience and are interested, come visit us and work with us. This is the nicest toolbox that you can ever have to play with nanoscience, electronic state to an acceptor electronic state. And my aim in this talk is to show you cases where Marcos theory does not hold, and where basically quantum effects are essential, and in particular, electron vibrational coupling is essential for basically explaining the physics that is seen. Okay, yeah. So I can go back to this molecule. Yeah. So very simple. Yeah. This is the donor, the porphyrin. This is the C60. Yeah. And I will tell you a little bit more about this. Specifically, it's absorption spectra, because we need them to basically excite the molecule. They show here bands that are associated to the porphyrin ring in the region around 600 nanometers. So basically, we can take red light to selectively excite the porphyrin region. Okay, and that's what we will do. And then I show you another result from this TDDFT simulation that puzzled the Modena people even more than us. That is the fractional charge, the time evolution of the fractional charge on the C60 region and on the porphyrin region. And you see that the electronic charge increases on the C60 with time. That's to be expected. That's the charge transfer. Yeah? But there were these oscillations here that they didn't understand, and we neither. And you see that on the porphyrin, there's a positive charging evolution evolving in a mirror-like fashion with the negative charging of the C60. So the donor becomes positively charged. Yeah? And the entire process was supposed to be happening on a 100 femtosecond time scale. This got us killed later in the refereeing process of the paper because other people who had worked on this system before thought that they knew that this charge transfer following Marcus' theory must be much slower and evolve on a picosecond time scale. Okay, but let's go on and let's do an experiment now, because we're experimentalists. Yeah? And what we do is very simple. We shine a short burst of light onto the sample. We call this a pump laser. This pump laser comes at time 0. Yeah? And then we probe how this pump laser changes the color of the system. We probe this change in color in a relatively broad spectral range with short laser pulses, in this case from 520 to 640 nanometer. And we probe this as a function of the time delay between this excitation pulse, this pump pulse, and this time delayed probe pulse. And when you do this, you see two things. Yeah? So first of all, you see that there are some bands that are oscillating in time. That's not a surprise, because basically the pump sets into motion the entire molecule. And so the molecule starts to vibrate, and high frequency vibrations are seen here, quote unquote, in real time as oscillations of the transmission spectra. Yeah? That's to be expected. And in this case here, it's the motion of the carotene, yeah, which does not contribute to the charge transfer process. But then there's another region here in the experiment, yeah, where basically you may or may not see that the color at which this molecule absorbs changes as a function of time. Okay, you see this better in the next plot. So you see one region here in the molecule at colors around 520 nanometer or so that oscillates very heavily. Yeah? And that's the boring thing. Yeah? So this does not matter for the charge transfer. The carotene is just set into motion, and you see the vibrational response of the molecule. But then you see another thing here, and that's this guy that shoots up here. You see that there is a band in the molecule that changes color as a function of time. You see this better now. I zoom into the first 100 femtoseconds. You see that this band that appears here increases in color as a function of time delay between the pump at 0 and the probe. Okay, good. So why do you see this? Well, you actually follow in the time domain now how the charge is getting separated in the molecule. This charge separation induces the local field in the molecule. This local field, this local electric field, induces a Stark effect. And this Stark effect shifts the color of the optical resonance. Okay? So by basically probing the color shift, you directly probe the charge evolution inside the molecule. That is the flow of the charge from the porphyrin to the C60. That looked nice, and we tested this idea. Yeah.
Just one question, Christoph. Someone asks, what is the pulse width of the excitation pulse?
It's just short. So here, for everything that is important, it's just important that the pulses are simply as short as possible, so that basically they do not wash out all the signatures. So if we want to probe 20 femtosecond vibrations, yeah, that means that the time resolution must be 10 femtoseconds. And that is why the experiments worked in our lab and not in other labs, because our pulses were so short that we could even see the fastest, the most high frequency vibrational modes of the system.
Okay, thank you.
Yeah, so here time resolution about 10 femtoseconds. Okay, good. And now you can now take a look at the time evolution of this central color of this band. Yeah? So the resonance position of the band as a function of time. You see a dramatic redshift. That's the redshift induced by the charge transfer process. Yeah? And interestingly, you see now that there are oscillations on this redshift occurring at 20 femtosecond or 25 femtosecond period. Yeah? And those were exactly the same oscillations as seen on the charge evolution on the C60 in the simulations. So basically, we found that somehow 25 femtosecond period or 23 femtosecond period vibrations, yeah, somehow were seen on the time evolution of the charge. So there's an interplay, that's at least what we can conclude, yeah, between nuclear motion, high frequency nuclear motion, yeah. So that's basically a CC stretch or breathing mode motion of the C60 ring, yeah, and that is playing a dominant role for the charge transfer. Yeah, and you can see this beautifully that this is indeed true. Yeah, by something that one can do in theory easier than in experiment, by just clamping some of or putting in place at fixed positions certain regions of the molecule. Yeah? And again, this clamping the linker region of the molecule, this Arrow ring, is sufficient to completely suppress the charge transfer process. Yeah? And if we fix all ions in place, then no charge moves whatsoever in the molecule. Yeah? So charge transfer is inherently driven by Vibronic coupling. It would not go otherwise. Okay? And that's basically what you see in the movie. And now as you follow, you can also, if you focus on the purple part here, you see that the charge has now transferred to the C60. Now it's flowing back a little bit. And if you wait a little longer, it will get more purplish again. Yeah. So basically you see a little bit difficult, yeah, in these movies, the coherent flow of charge between donor and acceptor. That's the beauty. Yeah. But most importantly, as soon as we stop vibrational motion, everything breaks apart. And that was a big surprise, and nobody believed us. Yeah? And we also did not believe our theory colleagues because we were very skeptical about the accuracy of those calculations. Yeah? So we were not really certain whether they would actually work. Yeah? But the result was quite striking. Okay, and so we went on and studied another prototypical case. Yeah? Again, something that is very similar to this molecule, but now a different donor and acceptor structure. We used again an organic molecule as donor. In this case, this guy is called P3HT. It's a polythiophene. It's typically used in solar cell materials. It's again an organic semiconductor that absorbs red light. And as electron acceptor, we used again C60 or PCBM, because if you mix PCBM and P3HT, you can form basically bulk heterojunction solar cell materials with an efficiency of the order of 8% or so. Yeah? So basically, if you're Italian, you can basically think about it like this. You have spaghetti here, that's the P3HT, yeah, and some meatballs mixed into this, and that's the C60, yeah. And this is an organic material here, and this C60 are inorganic electron acceptors that are so densely packed that basically the after charge separation charges are transported to the contacts of the solar cell through these C60 arrangements. Okay, if it's the entire structure, the active layer that we looked at is basically an organic thin film. It's approximately 100 nanometer thick. And if you look at it from the top with a scanning force microscope, you see that it disintegrates into domains. These domains are polymer rich or fullerene rich. And the usual picture is now that light absorption happens in the polymer rich regions. So basically, you create an electron hole pair in the organic semiconductor. Then this electron hole pair starts to move until it reaches an interface. And at this interface, basically charge separation appears, yeah, and creates a free electron and a free hole. The free electron can then move on through this percolated network of C60, and the hole can be transported to the contacts through the percolated polymer network. Okay, yeah. What's wrong with the picture? It looks appealing, yeah? But you see that, okay, if I go back, that there is a crucial intermediate step here, namely the electron hole pair that is generated in the polymer must be transported to the interface. Yeah? This electron hole pair, a typical Frankel exciton, is maybe 2 nanometers in size. This whole structure is maybe 50 nanometer in size, and it takes far too long for this exciton to actually move or diffuse to the interface to explain the efficiency of these devices. Because in this region here, it would just radiatively recombine. So that something else, something must be wrong with this traditional description, and that's what we wanted to figure out. Okay, good. So let's go to experiment again, and I have to introduce in particular Antonietta. She's a super smart postdoc who's responsible for much of the work. Now we want again to do this very simple pump probe spectroscopy. So we take pump pulses less than 10 femtosecond. Time resolution overall is less than 15 femtoseconds. So short enough to basically have access to all the fast vibrational modes of the system. And at this point, I have to thank Giulio Ciarullo from Milano because he helped us a lot with setting up such short pulses. let's look at the spectra. So this is basically the pump pulse and probe pulse spectrum. Yeah? And we excite in this spectral region the organic part of the system, the P3HT. Yeah? But basically the C60 absorption itself is very weak. Okay, good. What do we see? This actually, the left part here is the real experimental result. So you see there's time 0 here. That's when we excite the system. Yeah? And you can now see the change in transmission that at each wavelength from, say, 540 to 440 nanometers. And you can see, probably all of you can see this, that there's again coherent or temporal modulations, say it like this, of the transmission. So basically the color, the probability for absorbing light by the system changes periodically in time. And this periodic change in time reflects the vibrational motion of the system. Okay, good. So now, as an experimentalist, the first thing that you do once you see these oscillations is you perform a Fourier transform, because you want to find out who is oscillating there. Yeah? And then there are different regions in this entire spectrum. So first of all, there's this region here around 500 to 520 nanometer. And you can look at the data and you see that there is a vibrational mode that is excited. And this is excited at 1450 wave numbers. And that's the asymmetric CC stretch mode of the polymer. So the polymer starts to vibrate, and that's all. This is not particularly interesting. This is happening as expected, both in the blended film containing C60, but also in a regular polymer film containing no C60. So it just means that the light pulse impulsively excites the polymer, and in response to the optical excitation, the polymer does this. But what is more interesting and what was puzzling is the response in this region between 490 and 500, say. Because here, there's no vibrational action in the polymer itself, but if we fill in C60, we see that the system now oscillates at a different frequency. If we look at it carefully, it's 1417 wave numbers, and 1417 wave number is the pentagonal pinch mode of the full ring. So what is happening here is we excite the polymer, but it's not only the polymer that starts to vibrate, but it's also the C60 that coherently starts to vibrate. And that can only happen if there is a flow of charge from the polymer to the C60 within less than half a vibrational period. Because basically we need to impulsively or coherently excite the vibrational modes. And so there must be some extremely rapid coupling. And this coupling cannot just be a hopping within a few femtoseconds of the charges, because this would not explain the spectra. There must be an extremely strong coupling between P3HT, excited state, and C60, lowest unoccupied molecular orbital, to explain those observations. And again, the Modena people came up with a very nice movie that covers the physics. And this movie is done, and I want to try to explain this in a bit detail here in the following way. So you see that we have designed here a porphyrin, a thiophene ring structure. Basically, it's simulating in the simplest way a linear chain of this P3HT organic semiconductor, and it acts as a donor. And then we have placed on top of this a C60 molecule that is basically acting as the electron acceptor. And then we have put this entire unit cell into a periodic structure, forming essentially a crystal out of it, at least in the theory simulation, in order to prevent optical excitation to blow this dimer apart. Yeah? And in the simulations, we calculate the time evolution of the charge, but also simultaneously the time evolution of the nuclei. The time evolution of the nuclei is difficult to see because they don't move much, yeah? But they have a very strong effect on the charge evolution, as you will see in an instant. Yeah? And now we plot basically here in color code the excess charge that is generated by an optical excitation of the polymer as a function of time. And you see nicely the quantum coherent flow of charge between the P3HT region and the C60 as the cause. So basically, within the strong coupling regime, the electron nuclear coupling basically is the cause for strong electronic coupling between P3HT and C60. And this strong electronic coupling is basically causing the quantum coherent flow of charge between the two systems. Yeah? So actually, it's better to not think about this as a donor and acceptor as separate units, but rather as a donor-acceptor molecule, if you wish. Yeah? There's a relatively easy way that, again, to look at this. So here is plotted in the lower part, the time evolution of the energy levels of the HOMO, the highest occupied molecular orbital of the P3HT. That's not so interesting, but also of the lowest unoccupied molecular orbital of the P3HT, and that's the one that is involved in the charge transfer, this guy here. Okay, and you see it oscillates like this. There's also plotted the time evolution of the energy of this lowest unoccupied molecular orbital of the C60. That's the green curve. And you see at early times, directly after optical excitation, these guys here are not in resonance, they're detuned. And as you know from coupled harmonic oscillators, to detuned harmonic oscillators cannot couple to each other. There's no efficient energy flow. And thus, there's no charge transfer. The two are not in resonance. But now, the motion of the nuclei brings the two systems into resonance. And at this moment in time, once the electronic states are aligned, the charge can flow. The nuclei, we keep on moving, they lift the degeneracy between the states again, so this stops charge transfer, or brings them back in a periodic fashion in resonance, and this is causing the coherent oscillations of the charge. So it's a very super nice non-Born-Oppenheimer physics that we see here for the first time in the experiment, in the pump-probe experiment, and we see that the coupling between electrons and phonons is most essential for driving the charge transfer. And this coherent coupling is, of course, not included in Markov's theory. Really, or it means that any realistic description of charge transfer processes in nanostructures inevitably needs to take electrons and nuclear motion, needs to describe this at the same level. So both processes must be described at quantum level, and non-Born-Oppenheimer dynamics must be included in simulations. Okay.
Christoph, sorry for interrupting. There's one question right to that point where someone wants to ask, how does the spatial P3HT fullerene relative position impact on the charge transfer? I guess this question is motivated because we theorists in DFT always have problem getting these van der Waals bound systems right, as far as concerned.
We have tried to optimize this geometry, and of course, any variation in position that would necessarily occur in the real system would slightly change the energetics. So there will be disorder in this energy difference, but the important thing is that the system does not care about this disorder, because as you can see, the strength of the electron-phonon coupling is of the order of a few hundred millielectron volts. So even if this initial, level splitting here is changing by, say, 100 millielectron volt, the overall dynamics would not. This would induce phase shifts or so, but this is it's important that the electron-phonon coupling in the system is so strong that it dominates over basically disorder-induced effects on the level splitting. So you don't need to get the level ordering absolutely right. There's a certain tolerance, because again, electron-phonon coupling is so strong. Okay.
Okay. Thank you.
Good. So we have found a few cases, and in the meantime, a few more. So read our papers if you wish. Where we have shown that basically here quantum coherent coupling between electrons and nuclei is of central importance for charge transfer in artificial light harvesting in organic solar cell system. And by now, we pretty much believe DFT that it gets these aspects of the motion quite right. Now we have other evidence for this and new work. But that's a very interesting and extremely open field. So lots of contributions to be made there. Since we thought that we understood this, basically, I want to, at least in the third part of the talk, show you some new results where you can see that we're definitely not that smart. And I want to introduce into another aspect of electron-phonon couplings that is highly interesting, and that's conical intersections. But before this, I want to basically introduce, if I can, another spectroscopy technique that is very, very elegant and very helpful for shedding more light onto such coupling dynamics. And that is two-dimensional electronic spectroscopy. In this two-dimensional electronic spectroscopy, what you do is that you do not just take a single pulse, a single optical pulse here as the excitation pulse, but you use a pulse pair, a phase-locked pair of pulses with a certain time delay. Let's call it tau1 here. This pair excites the system under some angle, and the second pulse probes the system, and the second pulse is time delayed by some time delay tau2. One also calls this the waiting time in the experiment. Why the hell is this good? Well, let's look at the representation of a pulse pair separated by time tau1 in the frequency domain. So let's do a Fourier transformation. And you see, and you know this from your undergraduate courses already, that such a double pulse structure essentially gives rise to a comb-like frequency spectrum. And that is interesting now, because you can see that by choosing tau1, you can decide whether you want to have a minimum of the electric field amplitude at the position of, at the spectral position of a certain quantum emitter that you want to excite in your structure, or if you want to have a maximum. So when you tune this here gradually, yeah, from small tau1 to very large tau1, you will periodically excite or not excite a certain structure. And the periodicity is given by the color of this guy. Yeah? So you can, and that's the essence, you can use a sequence of 2 ultra-short pulses to selectively excite every single different quantum state in your system, and probe its response while maintaining time resolution set by the pulse duration. So you can perform, if you wish, a highly spectrally resolved experiment probing the fate of every state in your system with a time resolution that is only set by the pulse duration of the pulse. And that's pretty tricky, but very interesting. Yeah, and you can do nice things, because now, yeah, what is done in the experiment is, it's a bit complicated, but I will guide you through. So what is done is one records at a given tau2 time, at a given waiting time, a probe spectrum. So one maps the pulse-induced change in transmission of the probe pulse. So, and the probe pulse energy or the probe pulse color is called detection color. And one does this for a set of many, say 1,000 or so, different tau1 times time delays between this pulse pair. And then one performs a Fourier transform along this tau1 axis, and one plots the result as a function of the excitation color or excitation frequency. This will generate, you can ask me detailed questions about this later, this will generate an excitation frequency map and a signal frequency map, and this excitation or detection frequency map, this 2-dimensional map, contains most direct information about the density matrix of the system. It essentially contains along the diagonal of this map here, peaks that reflect each electronic state in the system. And then it contains off-diagonal elements, and these off-diagonal elements contain information about the coherence between the two states. So if, for example, there's an incoherent relaxation of energy between this state and that state, it would appear as one side peak that sort of varies in intensity as a function of time. But if two states are coherently coupled, pictures will appear in this 2-dimensional map with symmetric off-diagonal peaks, and these oscillate in time. And these oscillations in time give you some information about the coupling. That was abstract. I will show an example in a second.
So Christoph, this is called a 2D electronic spectroscopy because of the 2D map of excitation and signal frequency, not because some systems are 2D or something.
No, it's okay to be precise. Yeah, so this is an analog of 2-dimensional nuclear magnetic resonance, and 2-dimensional because basically you use a sequence of an excitation and a probe field, if you wish.
Okay, thank you.
Nothing to do with 2-dimension here for 2-dimensional material. There's also people doing 2-dimensional spectroscopy of 2-dimensional materials, but not here. Okay, quick introduction into conical dissection. Consider that you have a donor and an acceptor system that is now coupled to not just one vibrational mode, but to 2 vibrational modes. One being a symmetric and one being an antisymmetric one. Then basically the potential energy surfaces of donor and acceptor will show a very strange topology. They will, as is shown here schematically, they will meet somewhere, and there will be a region in the potential energy surface where they touch, where the potential energies curves touch each other. This region looks almost like a conus, and therefore this intersection of the two potential energy surfaces that appears in multidimensional potential energy diagrams, so multidimensional being several vibrational degrees of freedom, is called a conical intersection. You are probing conical intersections in the moment when watching this movie. Because in your eye, for example, there's a rhodopsin molecule. This rhodopsin is responsible for photon reception in the eye. And photon reception results in a isomerization process in the rhodopsin. And this isomerization process is driven by a conical intersection, for example. Okay, so here, we are now interested in studying whether conical intersections play a role for the charge carrier dynamics in organic semiconductors or not. The system that we study is the thin film aggregate. So it's very similar in principle to what we have studied before. Now the molecule looks a bit more complicated. It's not just a thiophene, but it's a donor acceptor ADA type molecules. So the structure is a little bit more complicated. In particular, this oligomer here, when you form thin films from it, it forms in the form of an aggregate. So basically, the two guys stack on top of each other, and such that basically they form an H aggregate. So if one is pointing in this direction, the other one is pointing in the other direction. So it's sort of as if you have two dipoles that are antiparallelly aligned. So that's the geometry of the system. And this antiparallel alignment of dipoles has the following consequence. So in this case, it's not the lowest excited electronic state that is optically bright, but the second excited electronic state that is bright. This will become important in a second. Okay, but so the absorption spectrum from the thin film looks very simple. There's a broad peak around 1.8 electron volts, and we probe this now with very short pulses in that with a spectrum that basically is marked in orange here. Again, this is a typical solar cell material. The chemists say this charge transfer is good to make this an efficient solar cell material. Efficiencies in the moment are on the order of 8% here, and it's nice and stable, has a broad absorption spectrum, but one does not understand why it works. That's pretty much similar to the P3HD PCBM case. And we were now basically based on our previous knowledge, we wanted to learn what the effect of vibrational coupling or vibronic coupling on charge transfer in this type of system is here. And so we did, as before, regular pump probe spectroscopy. You're used to this already, and this pump probe spectroscopy gives strange results. So time zero is here. That's why we excite. And you see that basically you see the impulsive excitation of the system. You see that there's oscillations. everything fine after a few hundred femtoseconds. But you see that in this region here, during the first 50 femtoseconds, this entire stuff looks a bit complicated. No? So you see this here, there's one band rising and decaying, the other one is slowly rising. Afterwards, everything is oscillating nicely, but this is strange here. And we didn't really understand this, so we zoomed in a little bit. And then the stuff becomes even more complicated because you have bands that are there at early times, but they vanish, and then some new bands appear, and this entire thing is quite a mess. And we did not understand this, so we went away from doing regular pump probe spectroscopy, and we used this new super tool that is called 2D spectroscopy. Now we can look at the 2D spectra of this material, and when you do this, you see, and I've tried to give you a primer on this, that there are some states here that appear along the diagonal. Okay? And they're always there. Yeah. Okay. Where does these side peaks come from? Well, such side peaks come and appear in the spectra if the electronic excitation is coupled to vibrational modes. So basically, this spacing here is the energy spacing between one high frequency vibrational mode in the system. And this somehow follows the Frank-Condon progression of this vibrational mode in the system. And these side peaks appear because of this coupling of the electronic system to the vibrations. You see them here. These side peaks oscillate in time. And from these oscillations, you can basically find out the coupling of the system to vibrational modes. Okay, so you see that here, during the first 24 femtoseconds, we are probing an electronic system which is strongly coupled to a high frequency vibrational mode. We can analyze this a little bit further in just a second, but that's about it. But now, look at the spectra, not after 24 femtoseconds after excitation with the pulse pair and probing with the pulse, but for longer time delays of the arrival of the pump pulse, of the probe pulse. So in this case, the probe pulse comes 45 femtoseconds, 60 femtoseconds, 90 femtoseconds, 120 femtoseconds later. And this entire nice structure that we have seen is completely gone. So that was very surprising, because we have launched this is what it seems to be. We have launched here an electron in some electronic state that nicely couples to vibrations. This electron in its electronic state continues to oscillate on. That's what we see when we analyze these guys in a bit more detail. But then after 40 femtoseconds, this guy decides to completely change its character and to stop talking to the same vibrations. So obviously, it must have changed, or the electronic nature of the excitation must have changed quite a bit. And as you will see, this is the signature of a wave packet that has just passed a conical intersection. For this, we analyze these guys a little more. We can now perform Fourier transforms. In these Fourier transforms, we can see the vibrational modes much more directly. And you can see that basically at early time, waiting times, our electronic system is coupling to one mode, and this mode changes even in frequency, so it becomes anharmonic. And then after 40 femtoseconds, all of a sudden, yeah, these vibrations change completely. Yeah? And yeah, so question is, what is this and how can this be? And to introduce this to you without going too much over time, yeah, I want to show you just the simulation. Yeah? And that's the simulation of an electronic wave packet that if we have placed on such a potential energy surface that is showing such a conical intersection. We launched the wave packet optically somewhere in the excited, optically bright excited state. Then we calculate its time evolution. It stays a nice Gaussian wave packet. But as soon as it reaches the conical intersection, it now sees a different electronic surface, and it basically spreads out in configuration or in phase space. Yeah? So it changes basically completely its position here. Yeah? And this spreading, that's what we have seen in the experiment. Okay. So now the question is, for the last 2 minutes, why the hell does this guy show a conical intersection, this substance? And for this, we again, as theory colleagues, we first started with Carlo Rozzi. We asked him about this, but he told us that this molecule does not show a conical intersection. So we started to collaborate with other people after some big fight with him. Yeah? And he was right, of course, yeah? Because we learned that it's not the molecule itself, but the dimer of the molecule that shows the conical intersection. So the conical intersection we are probing is an intermolecular conical intersection. Yeah? You have seen that basically these two molecules in a stacked form order in some antiparallel ordering, yeah? And this gives rise to a bright S2 state. So the second excited electronic state is optically bright, whereas the lowest electronic state, the S1 state, is optically dark. Yeah? Okay, and so what is happening now is basically, in theory tells us this, yeah, is this state is evolving for a few tens of femtoseconds on the optically bright surface, yeah, but then it jumps over by non-adiabatic coupling induced by the coupling to a strong antisymmetric vibrational mode of the system to the optically dark surface, and then afterwards oscillates on this surface. Huh? You can capture this in the form of a small little movie. So here we have sketched the conical intersection surface. There's also a third coordinate along which the system vibrates. So here we have followed how such a wave packet in a dimer is generated on an optically bright electronic state of the dimer, moves towards the conical intersection within 40 femtoseconds, and then by means of electron vibrational coupling, jumps reflectionless to the optically dark S1 state of this dimer, where it then localizes into excitons. And you have seen that the trick that we have played to analyze this process is again to use ultrafast coherent spectroscopy in this case, in particular, 2D electronic spectroscopy. So with this, it's time to conclude. Yeah? So here in this last part, we have seen a very peculiar result of electron-nuclear coupling. It's not just promoting charge transfer, but it's also driving basically relaxation processes in a directed manner between optically bright and optically dark potential energy surfaces. And that is what we have seen in the form of this intermolecular conical intersection that we've studied here in this organic thin film. So we have observed for the first time the results have just been accepted in Nature Nano an intermolecular conical intersection in a thin film oligomer. We have used two-dimensional electronic spectroscopy to track the coherent wave vector motion of this wave packet on the donor potential energy surface. And most interestingly, at least for us, we have really seen dramatic changes in the spectrum as a consequence of basically the rushing of this wave packet through this conical intersection. So for the first time, we really can track how such a wave packet changes in character when moving from the bright to the dark state surface. And we think that's a very promising result for future studies of directed energy transfer nanostructures. And with this, I want to conclude and thank you for your attention.
Thank you very much, Christoph. So I clap on behalf of all the participants we have here. I must say, personally, I enjoyed very much the fact that you kind of always brought your experimental work in so close contact with simulations and calculations. So I think there was really something for both experimentalists and theorists. Yeah, so it is that this was something which is very nice. So we have many questions. I think most of them will probably have to be asked in the special question and answer session, but there are some which I would like to point out right now. I start with a very quick one, because someone writes regarding the very end of your talk, I'm confused. If the exciton becomes from bright to dark, how can you detect it by optical spectroscopy?
Ah, okay. Good. Here, the bright and dark refers to the excitation process from the ground state. So we start in the ground state, and from the ground state, we can only excite it into the S2 state because that's the absorption spectrum. But now each of these states, of course, each of its excited state has an excited state absorption spectrum. And this differs from the absorption spectrum of the ground state. So we can promote it from state S2 to some higher excited state, or from state S1 to some higher excited state. In this excitation, the S1 state is not dark. And so we see the excited state absorption of the S1 state, but only, of course, after it has been generated. So we don't see it initially, so it's dark for the initial optical excitation, but we can see it as soon as it's formed.
Okay, very good. Then there is something which refers to the very beginning of your talk. I just read out the question, it's a bit long. You emphasize the role of high frequency modes. However, from processes such as charge transfer, low frequency modes can also be extremely important, as they can induce very large modulations of the electronic overlap between neighboring molecules. Does your approach allow you to characterize the role of these low frequency modes?
Yes, excellent question. Thanks for this. Yes, of course. Here in this organic system, the few examples that we have studied were all dominated by coupling to high frequency modes. So that's basically the strong optical phonon modes of the system. In other systems, I wanted to talk about perovskites at the end, but I don't have time for this. Maybe I can get some questions about this later this evening. There are none of these high frequency modes, and there the coupling is very much dominated by coupling to low frequency modes. And the important part, as mentioned in the question already, is of course that the oscillation period here is much longer, and therefore the field that can build up basically during one oscillation process also becomes longer. And yes, one can probe this by visible optical spectroscopy, but also by terahertz spectroscopy. So here, probing the effects of these high frequency modes by terahertz spectroscopy is not easy. That's really tricky. But for the low frequency modes, it's very easy, nice, and straightforward to see them by terahertz spectroscopy. We can also see them here, but the systems we have looked at here that I was discussing here, they simply did not play a dominant role.
Okay, and then perhaps one last question. I also read it out. It says, my question regards coherent charge transfer observed in the supramolecular triad and the OSC. One may argue that the coherent processes observed are due to the specific excitation condition, which means an impulsive photoexcitation. How do you expect the picture of coherent charge transfer to change under a more realistic excitation condition, for example, illumination by sunlight, which is directly relevant for the solar cell operation?
Okay. And that's again an interesting and highly relevant question. The important part is the coherence time of the light field. So for sunlight, these coherence times are very short. And that's the same thing as saying that initially the spectrum is very broad. So in our case, also, the spectrum of our light passes is essentially much broader than the line widths of the optical absorption resonances of the system. That's the same condition that is also fulfilled for sunlight. In this case, it is essentially the molecular system that acts as the spectral filter. So basically, what the molecule will do, due to the sharpness of the resonance, it will filter out the excitation spectrum, and basically only that part that overlaps with the absorption resonance will contribute. So in such a situation, both incoherent sunlight and ultra-short pulses basically give exactly the same dynamics. But with the sunlight, you cannot probe this in the time domain directly. No? But here, in those situations where the pulses are really so short, there's actually no difference to be expected between sunlight excitation and impulsive light excitation, unless strong field effects on the excitation, so its effects of a very strong laser field, are becoming important. But there's not very many very detailed experimental studies of this. It's an excellent question.
Okay, so thank you very much, Christoph. And so I have to say that all the other questions, they would all be worth being asked. And I refer every one of you to what happens this evening, in fact, when there's the question and answer. And you already know from yesterday that there will have much more time to have questions and long answers, and we can discuss all the things which unfortunately now remain open. Okay, so thank you very much again, Christoph, and see you later for the Q&A. So before I give the floor to Nicola Seriani, who will chair the second part or the second talk, I would like to use the fact that right now there are many people connected. So I would like to say something about the poster session tomorrow. So tomorrow we have a poster session. A poster is, so to say, posters. It will be online posters, obviously. And it will work in the following way, that at the allotted time, we all connect, in fact, to this Zoom room. So where we are now, you all connect. And then those people who present a poster, they will have, say, 1 or 2 minutes to say what their poster is about. So the presenters can, if they want, show one slide, but please not more than one slide. So it's not to make a talk about your poster, but just to say to everyone what your poster is all about and make people interested in your poster. Okay? So this will be something, so we will have, I think, 28 posters in the first session. So this will be perhaps an hour or so in total. And after that, we will have a lot of different Zoom rooms. You will get the addresses where everyone can connect to that poster or that topic one is most interested in and talk to the presenter there. So this is the idea how we would like to do it, both for the first and for the second poster session tomorrow. Just a little technical information. So the poster sessions always start in this Zoom room with these access credentials. Okay, so that was all. Thanks a lot again to the first speaker, and the floor is for Nicola, who will introduce now the second speaker.
So good morning, good afternoon, and good evening. So we are now going back to theory, but we are still be hearing about molecules with Alessandro Troisi from the University of Liverpool. So I think we go straight to the talk. So please, Alessandro, the stage is yours. Thank you. Alessandro, you're muted.
Hello, hi. Just got disconnected, but I think that's how things work. Wait a second, share screen. Can you see this?
Yes, yes.
Sorry, I missed the last 30 seconds. So if this was the introduction and I could start, please say that again.
I just said your name and an affiliation. So yes. So you can start. You can start whenever you're ready. Yes.
Great. So thanks again. So for the invitation, thanks to Ralph and Nicola for the opportunity to talk here. I think I'm enjoying these events because of diversity and the geography of all the participants. So it was a great question session yesterday, and I'm looking forward to the next few events. I'll be presenting from Liverpool, where I moved a few years ago, 3 years ago, to this building. It's called the Materials Innovation Factory, and I want to connect somehow the talk I'm giving to my move there, because it's always a good idea to move mid-career to change perspective. And the idea of the institute is to discover new materials through robotics and automation, so people making things and measuring things automatically, and then to have models and computer guiding the discovery of new materials. So the point, if you are a theoretician like myself or a person doing modeling, is to find the best way to build models to discover new materials. So this is something that may happen to many people in the audience if they go to work for a company or to a new institute like this one. And so the talk will be about comparing different approaches to discovering new materials. And I like to go through 3 different ways with 3 different set of examples. Even we can go through, let's have a lighter pointer there. We can even go through high-throughput screening, what we can call a brute force approach. We just compute things, hoping that they are correct enough, that they can help experimentally pick the right materials. Or we can do something maybe more subtle, maybe not, we'll discuss, which is using data science, collecting more data and using maybe artificial intelligence to do the work. Or we can go the old-fashioned way. We can build a bottom-up model, basically go to the library, read a few books, and build models to understand what's going on. And the idea of this talk is to use different domain or problems for each topic. So there will be 3 methodology and 3 area of interest, so it could be kind of complicated. However, I will try to keep everything light, and my idea is to spend about half an hour on the first 2 topics, maybe stop to check that the timing is correct, and then ask a few questions before going to the last one. So it's not too boring or listening just to my voice. So the 3 topics are singlet fission, organic photovoltaics we heard about, and transport we heard yesterday about. So the first problem I want to consider, I put it there because it doesn't really require much background, is predicting material which are useful for singlet fission. Singlet fission is a process where you excite the first single excited state of a molecule, or maybe you get there through other means. And the singlet state, which can naively represent in this way, will generate 2 triplet states because the energy is such that this is energy favorable. So the energy of the triplet is less than half the energy of the singlet. This process is spin allowed if the electrons are correctly aligned. And it's very interesting because you can generate 2 exciton from 1 photon. Therefore, you can create a solar cell with higher efficiency, and this has been proved. Lots of theoretical interest in this topic, so there is a review if you're interested in it, but a lot of interest from people trying to design material from single fission. So if you look at the literature, many of the highly cited papers talk about mechanism or strategy to search for material with these properties. So material with the very low lying triplet, such that the energy of twice the triplet is less than the energy of the singlet. So search, seeking, and one of the main idea is to build or search for molecules which have a diradical character, because the idea is that the diradical molecule has a triplet energy very close to that of the ground state singlet, and therefore may be suitable for this type of material. So as we mentioned in my cartoon, one approach is to go brute force, meaning ignoring everything we know, or even the interesting insights of smart people, and just look for material with a decided property from a database. So it's the dullest possible way of doing things. However, if it works, the smarter way become, if you want, less relevant. So what we decide to do first is to make sure that we can compute the energy of singlet and triplet accurately enough. And so the first thing we do every time we want to convince experimentalists to follow our suggestion is to calibrate the experiment, our theory against the experiment. And so we make a plot of computed singlet energies versus experimental singlet energy for a medium-sized database. It was 100 molecules in the appropriate range for singlet and triplet to show that our calculation is decent enough. The slope is not 1, and there is also an adjustment factor there, but we can use this calibration to actually make a prediction which is calibrated against the experiment. So we don't use the error as a negative, but as a positive to improve the discrepancy between predicted and experimental excitation energy. Once we convince ourselves that we can measure these properties, we need a data set. We need a data set of molecular semiconductors. And so we all know, also from yesterday's talk of high throughput, that one of the most difficult things to do is to optimize the geometry or find the right geometry. Therefore, one thing we did was to consider example of molecules that we know the geometry of, so we don't have, at least in the first instance, to find the right geometry and optimize them. So we can see the 1 million structures that are available from the Cambridge Structural Database. And from this huge set of structures, most of them are drugs, completely relevant for our properties. We identify 40,000 molecules which are semiconductor in quotation, because they're not really semiconductor as molecule, but they have an HOMO-LUMO gap, which is small enough. And in the field of semiconductor, this is a number which is considered suitable. In organic, of course, this number is smaller. So once we have 40,000 molecules that we identify to be interesting, so conjugated, you can excite them with visible or near UV light. We look for molecules with the suitable energy levels so that they could undergo singlet fission. And so we computed energy of the triplet, the energy of the singlet. Here we report a doubled energy of the triplet. And so all molecules which have energy of the singlet slightly larger than double the energy of the triplet are potential candidates for singlet fission. Those are based on the crystal structure geometry of the molecule. Then, of course, we take our candidate, we optimize them, we perform the higher level calculation, and we end up with a very decent number of molecules which are predicted to undergo singlet fission. So, of course, it looks pretty straightforward, although it takes some time, not to mention learning how to automatically input this into the code. And but the throughput is kind of impressive because we have 250 new potential single fission molecules, and about 10 are known so far if we exclude molecules which are just simple modification of already known molecule. So brute force sometimes is the way to go, especially when the properties are easy to compute and when there is no controversy on the connection between what you compute and what you measure, because you can calibrate your data very nicely. And so one condition of this high throughput method is that you find already known materials. So for example, what I have indicated here in black are molecules that are known to undergo single fission. And the approach is interesting if you also find something which is not known, or start the study of completely new material in these categories. And so we have the majority of molecules we find are in this group. Of course, one of the interesting part of moving to this new institute is there, which is actually the virtual screen is how it looks from inside, is that we also can do some experiments. And so for the first time in my life, I was so convinced about the prediction because of the calibration that we decided to actually test it. And so we reached the point of buying molecules. We have a couple of molecules having made for us, but fortunately, maybe for you and for me, COVID arrived before we could actually measure this. And so it will be for the next time to test specifically the idea. However, the idea are, in a way, the calculations are self-testing because we already found within the data set material that are already known to be single fission materials. Once you have your result, you cannot stop trying to answer questions yourself from trying to answer questions that are out there in the literature. And since the literature of single fission is dominated by the idea that single fission material are typically biradical, one interesting analysis that you can do is to check if this is true once you have generated a much larger set of potential single fission material. So you can plot the propensity of doing single fission versus the radical character, and then the generally acknowledged truth is that material which are potentially single fission material are in this region, so have good radical character. And what is the rule is essentially this region there. But we also could find some exception. So material that don't have a radical character, some of them have charge transfer character, some of them we don't really know. And so once you do your high throughput screening, the exception becomes the topic of your next paper, essentially, and you leave the materials discovery business and you enter into the more physical chemistry or physics business, where you analyze your result and try to find new correlation or new explanation. So this paper explained why this material may be interesting and not have a radical character. Then, if you work with database, a large data set, you want to also accelerate the possibility of testing. And so a small tool that we made as an aside from this project is allow you to, once you find a molecule which has potentially interesting properties, search a huge database of several minion structures which you can actually buy for molecules that are easily, that are cheap, that you can buy within 2 weeks, that can be used to test the ideas. So what we have now is a methodology to look for interesting properties that are of molecular nature for photophysics, photochemistry, and so on. And once we've identified interesting molecule from the data set of crystallographically available molecule, we can also look for very similar molecule with similar connectivity, similar conjugated core that are actually commercially available. And so if you're interested in looking for a special property, I don't know, room temperature phosphorescence, toward fluorescence, up conversion, and so on, we can work together on this. So my main point of this high throughput screening part was to stress two aspects, which essentially I learned as I moved into this business, is that the quality of quantum chemistry of computational physics is now less decisive. In a similar meeting on ICTP, maybe 15, 20 years ago, people were discussing about the relative merit of different DFT implementation. Mine is better than yours, and so on. It's not accurate enough, and so on. And still, in several areas, for example, organic-inorganic interface, that's a very interesting research topic. But whenever you move more into the well-established chemical space, there is no reason anymore to discuss about the quality of the density functional, because you can actually calibrate against a large data set of experiments. So there's not the quality is not a mystery. It's something that you can actually measure and be part of your prediction. Another thing which actually becomes more interesting, especially if the P in ICTP stands for physics, is that once you have data and you compute the property, you can test hypotheses. And the testing of the hypothesis is much easier if you have a sufficiently large data set, and if you have generated the data set automatically, then it's unbiased, and then the way you test the hypothesis is much more valid. And so we can take this one step forward and see if from data we can extract physics without the intervention of human, which is something very worrying for everybody with a degree in physics. But this is something we actually need to face and to deal with and understand what is the newer role of physics in a world where we can use data to bypass the construction of model. So I will give example of this in the context of organic photovoltaics. And this has been beautifully introduced by Professor Lineau before me, so I don't have to explain the details. I just say that I've been working in this as a traditional physical person modeler in the fairly obvious way, which is building a detailed model of the system. In our case, we use molecular dynamics simulation to build an interface between donor and acceptor. This is the P3HT that Christoph showed before. It is the PCBM, or essentially Fullering derivatives. So we looked at this interface in details, a lot of work to do this. Then we build a reduced model, a model Hamiltonian, which should represent this idealized model to describe how the charge is separated in an organic photovoltaic device. And from the rapidity of going through this to the cartoon, it's obvious I'm not going to talk about any of the details. What I will spend a few seconds to say is that we use this traditional reductionist bottom-up model to make predictions. And one of the prediction was the following. We predicted, so we put the prediction in the title very boldly, that you can replace fullerene in a solar cell with molecule made in this way. Molecule which were dimer of other molecules which were well-known electron acceptor. We did this a few years back, and weeks after this prediction, what at the time was the top performing solar cell with acceptor which were not fullerene came up, which was exactly dimer of the same molecule we predicted a few weeks before. So now, as a physicist, you have the following issue now. Are you just looking at examples that confirm your own theory, or is your prediction truly valid? And this confirmation bias is something we cannot do without. It's really human nature. And so it's common throughout literature that any idea is constantly reinforced by example that prove that the idea is valid, but any counterexample are typically not discussed as attentively, let's say. And so what we can do with data is essentially not to look at individual item from the literature, but look at the literature as a whole and check if one particular idea was valid or not. So in this particular case, our idea was that an electron acceptor for organic photovoltaics is good if the energy separation between LUMO and LUMO plus 1, the computed LUMO and LUMO plus 1, are small. So the idea was that when we put this characteristic in the model Hamiltonian, the charge generation is much more efficient, while if LUMO is slightly too large, there is some sort of anti-tunneling effect, so that depress the rate of charge separation. It doesn't matter if the model is right or wrong. What does matter is now we can actually collect, a few years later, data from the literature to see if the best electron acceptor have these properties. So what we do in this case, when we need to collect data, we resort to undergraduate students, which are particularly cheap to for trivial type of activities, and they know more chemistry than most of the people in my group. And so in this case, Alina spent a few weeks looking at the literature and collecting 79 high efficiency acceptors that appear in the literature, and try to see if there is a correlation between having a small LUMO to LUMO plus 1 gap and having a high efficiency. So the result of her work is there. The typical delta LUMO energy computed with the same level of theory, which at the moment I don't remember actually, is between 0.6 and 1 EV, taken from a literature review that appeared in 2011, while all the recent electron accepting material have a very small delta LUMO gap, with the very best material accumulating in the region of the very small delta LUMO gap. So it doesn't matter if the model we propose is right or wrong. Now there is an empirical evidence that having a small delta LUMO is beneficial for materials with high efficiency, high efficient as electron acceptor in solar cell. So this was a physical idea coming from the model and then verified through the data. So the question is, can we actually bypass completely the physical thinking and the model and go directly from the data to extract useful prediction? That's the idea. So we could, in principle, build models without physics, and we should hope that they are actually worse than the model that the physicists will develop. Otherwise, we would be out of job. So the idea is that we can take a set of experiments, in some way we transform them into data, and it's not trivial at all, because of course the experiment is not described by a real variable. It's lots of discrete description of the experiment, and the chemistry is not obvious, and so on. And then a machine learning algorithm is essentially is informed by this data and allow you to predict the outcome of proposed experiment using the data that have been used to essentially train the algorithm. The experiment now need to be collected from literature. The way to read automatic literature is not good enough, and so it's a tedious task. There are interesting data sets available, but they're also almost never exactly what you want. In the data that describe the experiment are the physical condition of the experiment, but also the composition of matter of the experiment, so the chemical structure of the component of the experiment, a combination of both, of course. The easiest part of all is the algorithm. It's easy because the algorithm is itself easy, it contains its own Wikipedia page, you can implement it, but it's also easy because there are packages that have this already implemented, so the entry barrier for performing machine learning is extremely low. That's why there is a propagation of this technique very, very rapid. Then, of course, you can use a hypothetical experiment to decide what will happen in the future, but then you don't know if the prediction is good or bad. But the most common approach is to simply consider some of the existing experiments, remove them from the data set, and use them to see how good the prediction would have been if those data were not available. So that's the idea, and you will find this many reviews around. And so we wanted to check if it's possible to use the same idea to predict the efficiency in organic solar cell. I was fortunate enough to be involved into two projects trying to do exactly the same, but with two different teams. One was led by Haiboma and Nanjing, and so I essentially was almost a spectator of this project. And the other one was done by Daniele Padula in my group, now in Siena as an assistant professor. And that's what I'm going to talk about. But the initial message is that the two algorithms look completely different. The data set is similar. the output is of similar quality, but also it looks very different. So there is an element of a lack of control of what you get. And so people tend to focus on the correlation or the root mean square error. And the typical quality of this prediction now will have this type of correlation of 0.7 correlation factor. And this is also when you consider work by other people. Let me say something more about how we did this. We use a kernel ridge regression method. The idea is that you collect the descriptor of your system into an array, the set of descriptor. Your figure of merit will be the efficiency. You define some sort of distance between system. So the idea is that if two systems are identical, they have the same efficiency. And there is a formula which really looks like a regression. It's slightly modified by the nonlinear definition of distance that allow you to predict the efficiency for a new set of descriptor. So this box is how you will find KRR described in a textbook. And then essentially, when we apply this to organic solar cell, it will have as an input the chemical fingerprint, a description of the chemistry of your system, the orbital levels, organization energy, and then the efficiency is there. Essentially, you change the high-throughput parameters until you find a method which gives the best description of future observation, where future is pretend future. So the idea is that it's not much different than an interpolation. And so you normally want to ask if this is good for physics. My preliminary answer to this question is that if an interpolation does better than a physical model, then the physical model is not good enough, it's not informative enough. And so again, if you have not understood the physics and the linear extrapolation works good, then of course it doesn't bear very well for the quality of your understanding. So in some way, this approach can be considered as creating the baseline for what can be considered as good physical model. We also wanted to use this type of approach to help the development of physical model. So to, from the fitting or from machine learning, understand what is really important in a system and what's not. Unfortunately, it doesn't work. I will say just briefly the outcome, but when we try to increase the number of physical descriptors and we add descriptors which were highly correlated with the efficiency, adding this descriptor does not improve the algorithm. And the reason is that the description of the chemistry of the system is already good enough to describe the efficiency. In this graph, I show how the accuracy of the model if we include only physical parameters, if we include only chemical parameters, and if we include physical and chemical parameters. So what you see is that the model, doesn't matter the details of the model you use, is already as good as you can get when you introduce the chemical descriptor of the system, which essentially imply, if you want to be very negative, that if you want to predict the efficiency of a solar cell, and you give the problem to a person with a background in pharmacy, where they try to find correlation between drug and efficiency, but just by looking at the chemistry, without knowing exactly how it works, the pharmacist will make the prediction, which is just as good as the prediction that the physicist will do. And so in a way, there is so much information in the chemistry that the extra physical information that you add will not help at all, and you're unable to decide what physical information is important to describe the system. I think, well, I'll say this just to exemplify that there is an element of fun into doing this type of analysis. And one element of fun is that if you look at all donors that have been considered and all acceptors, you will find that here all dots correspond to point where there is a corresponding donor and acceptor. You will find that there are very few instances where in the majority of cases, the donor is tested with only few acceptors, and the acceptor is tested with only few donors. So it would be nice to have a mechanism to predict what would be the efficiency of a new combination of donor and acceptor. And the interesting thing of machine learning is that you can take a beautiful algorithm from the field. And of course, the field is reached by, is dominated by social media and technology platform. And so this problem is essentially a problem that has been solved by Netflix, because in Netflix, they really want to predict as efficiently as possible what is your favorite movies based on how you ranked the movie that you've seen and how other people have ranked the movie that they've seen, and the two sets do not overlap very well. So this is a matrix completion problem, and so you can use the same Netflix algorithm to make prediction of the solar cell made by new donor and acceptor combination. And actually the prediction is better than the prediction where we only change the donor or we only change the acceptor. So I want to stop there about artificial intelligence. And so maybe I can take one or two questions about that before moving to the more physical part of the talk, which is the last 20 minutes.
Yeah. So I don't know, Nicola.
Sorry, yes, I was muted.
Okay.
Yes, there is a question about the first part, the singlet fission. So for singlet fission to be useful, you must prevent exciton-exciton annihilation between the two excitons you produced. What are the conditions to prevent this? Did you take these conditions into account in your calculations?
Essentially, we've seen it already. It's a computational funnel problem, and the order by which you do it is the largest narrowing of the funnel goes first. And so here the largest narrowing is from all structure to semiconductor. Then the second largest is for semiconductor to potential singlet fission. Then for the annihilation, of course, then it becomes a problem by problem situation. So we end up with a data set which is 200. And so for those 200, we can look at the details. So when we look with when we talk with experimentalists, even before annihilation, there is another thing that emerges. For example, is safety. So this material is toxic and so on. So there will be another narrowing down to the of the chemistry you can use. And then when you reach that point, then you do traditional modeling where you consider the other channel. There is not only the annihilation, there is also the triplet combination if there are two triplets that are at the right energy level. So we didn't reach that point, but before we reach the point, there is an extra level of going into the experimental world. And so that one is proven to be more difficult than we expected. So the experimental constraints are stronger than other physical constraints, let's say.
Okay, so I think we can leave the other for later, for the end of that.
Yeah, it was good. It was also to check last time I left more or less, and so I will paste the continuation accordingly. So let's look at a little bit of physics now and see if it's on occasion is required or necessary to use a physics-based model. And I'm going to use one of my favorite topics, is the transport in molecular crystals, something that I've been working for many years. So there will be a few slides about the past and maybe a few more slides about the present. These are materials, of course, are molecular crystal, and the main things to know is that if you measure the mobility, you get a number of the order of 1 centimeter square per volt per second. And then when you take this number into account and go to the library, you immediately realize that this number is not consistent with a mechanism of transport where the charge hops from molecule to molecule, because it's just too fast. It will imply that the molecule will move more quickly, the charge will move more quickly than the vibration. That's not really possible. But it's also not possible to use a band type of transport or Boltzmann theory, for example, because it will imply that the scattering between two, the distance between two scattering events is actually shorter than the distance between molecules. So this small mobility is not even consistent with the localized transport because the scattering is just too frequent, or if you prefer, it's beyond the Joffe-Regel criterion for scattering. This is a cartoon to show what's happening. We know that if two hydrogen atoms interact, they form a bonding and anti-bonding orbital. And when we consider molecular crystal, the best basis set to describe the orbital there is the localized orbital on each molecule. So when I put two molecules together, the HOMO level, I'm looking at transport of positive charge, will split into two. And when I consider an array of them, I generate a band. The band is really a narrow band generated by one orbital. And so we have a model which is electronically very, very simple. It's simple from the point of view of the dimensionality, not so simple from the point of view of what affects the interaction. It was a question by, I think, Antonius of the previous talk. The coupling between two molecules, the overlap, depends very, very subtly on the relative motion of the two. So you just need a small displacement and the coupling goes from one sign to the opposite sign. And so what you have is a situation where just thermal motion of the molecule will change the interaction between them, the coupling between them. In a very old paper, I think this was my first paper when I was appointed as an assistant professor. If you do a molecular dynamic simulation of a crystal and you compute as a function of time the transfer integral between two molecules, so the overlap between two molecules, if you want, there is the fluctuation due to thermal motion is enormous. It's actually almost as large as the average value of the coupling. The implication is that if you have to freeze, if you could freeze the crystal at one point in time and compute the eigenstate, those will be localized. So the situation explains why the scattering is so frequent. Essentially, the coupling with the non-local electron from coupling is very large. So the coupling of the electrons or the holes with the motion of a molecule. A cartoon that explains the mobility was proposed more or less at the same time. And you can imagine that the electron or the charge is moving and the lattice is oscillating with large amplitude oscillation, more or less with the same time scale of electron passing through it. So it's not possible to do the time scale separation. That's why band fails. That's why the mobility is so small. This idea has some traction, and now in the literature of organic molecular crystals, molecular semiconductor, the idea that to have the best semiconductor, you need to reduce what we call a dynamic disorder is now accepted. And so various papers focus on either on measuring it or in rationalizing the performance of materials on the basis of reducing large amplitude motion or reducing dynamic disorder and so forth. As you can imagine, when you translate this idea into a model Hamiltonian, we saw them from Bernardi's talk yesterday and also from Oleg Prexdel. This problem is very standard in the mathematical form, but it becomes non-standard if you put the number in it. What makes it non-standard is that the bands are very narrow and they have the same order of magnitude of the phonon that are strongly coupled to them, and they are not very different from the room temperature typical energies. Therefore, we have a situation where all relative magnitudes are, all matrix elements have similar magnitudes. We cannot really derive a nice perturbative approach to transport. So we need to resort to integrating the equation of motion. And so we had from Oleg Prexdel how you can do it. And essentially everybody with an idea of how to perform quantum dynamics jumped into this problem, had their own version of how to address this problem. And so almost impossible to summarize, but we tried in a recent review. So if you're interested into knowing the background and various approaches to study dynamics of charge when the molecule move at the same time scale as the charge move, you can have a look at this very recent perspective paper. However, if we want to discover new material, we cannot afford to do quantum dynamics of a large set of materials. So we need something quicker, but possibly also accurate. So the solution came by a team, Frattini and Sergio Ciucchi, Grenoble and L'Aquila, that actually were able to come up with essentially an analytical, quasi-analytical formulation of the problem. And they were able to express the mobility through a closed formula. You know that you can see that the units are right. And essentially the mobility depends on the what they call the transient localization length, which is a measure of how localized the states are because of the dynamic disorder, and the time scale of these fluctuations. I just look at the time and I will not explain the model. However, we have a question and answer section later, so we can go to that. But the idea is that now, with an expression like this, we can study 1,000, as many systems as we like. And what we decided to do was to build a map of all possible semiconductors. So we essentially looked around at what is out there and noticed that in all semiconductors, we have a molecule coupled to essentially 3 neighbors, sometimes 2, but this does not change the generality of the model. And we compute the mobility for all possible coupling that you can have between molecules using experimental range as a guide to what was relevant and was not. So what we came up with is essentially a map, a one-to-one correspondence between all possible molecular semiconductors and point in a sphere, on a sphere. So each point corresponds to one particular arrangement of transfer integral between neighboring molecules. So this point here corresponds to transfer integral A, B, and C, which are similar in sign and size. This point here is corresponds to a point where JA is large and JB and JC are very small or 0. And the color on this map indicate whether the mobility is large or small. And so there are interesting results. Let's say there are trivial results, for example, that one-dimensional material are not very good for mobility and that isotropic material are much better. But also something totally unexpected, which is, for example, that if you change the sign of one of the coupling, you end up there. So if you change the sign of JA, the material is not good anymore. So this is a qualitative map, we thought, that could describe what you should do to have good material. However, when we submitted this to the journal, they say, well, why don't you show some experiment on top? Because, of course, as all tradition, we believe experiment ruin the theory. And so we had to go back and search for experiment where intrinsic mobility was proven. And essentially what we find is that this model has a predictive ability that actually it was beyond what we expected. And so if we consider a set of 4 materials which have been made by the same person in the same lab, we realize that the model predicts the correct order and scale of the mobility between them. And when we look at the broader range of materials and we put them on the map, this is just a section of the map, we realize that the general set of high performance material with intrinsic mobility falls very well within the trend. So the last step is that we need to, if we want to predict properties, it's not enough to just look at the relative sign or relative size of the coupling between coupling. We also need to compute the electron phonon coupling because, of course, the disorder, whether it's large or small, will affect the coupling. So the last step we have to do, after reducing the total set of molecules from 1 million to 40,000, and after using the map to identify the best 5,000 potentially high mobility material, is to compute the electron phonon coupling. So what we did, and so I'll go quick because I see that I'm running more or less out of time, was to develop an accelerated methodology to compute the electron phonon coupling for up to 5,000 or this order of magnitude molecules. So we checked, well, I'll skip this. So we have a very good way of computing it accurately. So the problem was to compute it approximately. So we create an approximation where a molecule is surrounded by rigid molecules, which are described only classically. So essentially, we use the QMMM approach to describe the phonon of the molecule. We validated it. And so we concluded with the computation of the mobility, the predicted mobility of the most promising 4,000 materials. So when you reach this, we thought it was impossible. It took many years to do. And of course, you are tempted to do different things. One is to look at the high-performing one to just suggest the experimentalists to perform a testing. But then, and I'll show a few examples in a second, but you also want to understand what makes the best, and so whether you can find a way to improve them even further. And so what we discovered is that we consider the mobility as a function of all possible components that can affect the mobility. And we realized that the most important ingredient that makes the mobility high is actually quite trivial, is the unit cell area. Because in a model where you have one orbital per molecule, if the molecules are more separated from each other, the mobility increases as the square of the area of the unit cell. Then the most important parameter before we did this work is still there, is the second most important, is the non-local electron phonon coupling, the fluctuation of the molecule, the thermal fluctuation. And the third one is what emerged from the map, which is essentially you want a more isotropic band because 1D is very bad for transport. Maybe I would like to make just one point slowly before going to the conclusion, is that once you look at the data set, these are a few examples of high-performance molecule, what we discover, and possibly the most important discovery of this high-throughput screening, is that the best material don't tick all the boxes. So if you look at the top mobility material, and we color in green if one particular property is ideal, and in yellow or red if it's not ideal, we realize that the top material are not ideal with respect to all possible properties. This means that there is a room for improvement, and you can actually use the data set to decide what is the maximum achievable mobility for this set of material. First, you need to check that all the components that contribute to mobility are uncorrelated, otherwise you cannot improve one independent from the other. And then you can perform a hypothetical experiment where you improve all components, all contributors to the mobility in such a way that you simulate the generation of an ideal material within the realistically available range. This is, I think, is my last slide. So we show, no time to look into the number, that there is no correlation between parameters that affect the mobility. However, and for this reason, we can create an hypothetical experiment where we take all the parameters and we make them better in parallel within reasonable range. So this is the mobility that we will get if all parameters were set to be in the top 15 percentile, 10 percentile, or 5 percentile. And this is the type of improvement that we expect as physically possible and statistically possible from the data set of material. So we can actually not only make prediction of selected material, we can also set the achievable target for the entire class of material because we have looked at all of them, so we know what is achievable in terms of parameter for each one of them. So I'll use this as a conclusion and I'll skip the last one. The conclusion is that we have to introduce an extra technology innovation to be able to compute electron phonon coupling for thousands of systems. And coupled with translocalization theory, we can identify high mobility materials. And if there is time in the question, I can also give example of design rules or idea of how to design new materials that come from this work. Which is a slide I'm skipping. And this is the summary with a key paper that if you want to have a look. And I'm happy to answer a short question now and longer question later.
Thank you. Thank you, Alessandro. Let's start with, as he puts it, a provocative question. So he has the impression that you used artificial intelligence purposely to predict without understanding. Isn't it deceiving as a physicist?
Yeah, I wanted to expand this. I think normally I'm the provocative person. So essentially, what is happening is that jobs are actually moving from people with a degree in physics to people with a degree in computational science. And this happened to us, it's happened to our collaborators, it's happened to the UK as a funding team. So now it's very likely that a company working on the advanced material will collaborate with a computer scientist and to a physicist, even if they are developing a material. So this lack of understanding of some matter is something we should stress to really defend our job as a community. So you need to understand in order to be able to interpret. I believe it's not possible to do anything productive without understanding. However, I actually stress this point because that's what's happening. So people outside this community are hiring computer scientists to do our job. So I wanted to stress this point rather than, but my point is, yeah, we need to defend our job. We need ourselves. So
this is my personal comment. So if I understand correctly, we are getting much better, or people are getting much better at interpolation, if you want. So this is having a huge impact. But of course, it's I mean, you will need understanding if you want paradigm changes. If you want to develop completely different approaches, you will still need the real physics. So.
Exactly. And so let's keep mentioning ideas like semiconductor. They don't exist in nature. They've been invented by us just by looking at the blackboard. Let's mention it, polymer. They don't exist in nature the way we make them. They've been designed on the blackboard and so on. So we have all these paradigm change that are not possibly made from interpolation. The periodic table is another one. Yeah, I cannot imagine the computer will ever come up with a way of arranging the element in that way. So we need to remind ourselves of how good we are. And so we use the technique without undermining our position.
Thank you. So now we go to some more physical questions. So can you explain in more detail how you compute the approximate mobility? I guess this is about the
yes.
classical.
Yeah, so it was proposed by Frattini, so it's not my method, but it was initially proposed as a approximate method that happened to be more accurate than it was anticipated by the authors themselves. So the idea is the following. We start with something which is correct, essentially using the Green-Kubo formula for transport, which say that the mobility can be computed by the correlation function of the current correlation function. So what they say is, okay, we know this correlation function at time 0 because it's the correlation function of a disordered material. And we know that it's going to decrease to 0 through some relaxation time. So what they did was just write an approximate correlation time with the relaxation time t, which is essentially based on the fluctuation of the transfer integral, and using the time 0 correlation function of the disordered material, essentially Anderson localization due to off-diagonal disorder. So with one parameter, which is constantly taken as 1 picosecond because all this fluctuation takes at a time, you just build many disordered metrics and you plug what you find into this closed equation. So it's a relaxation time where instead of assuming that the natural state is the particle in a state K moving freely, you assume that the reference state is instead the fully localized state because of dynamic disorder. So it's the same Boltzmann idea, but reverting what is initial and what is final state.
Okay, thank you. So in the where you said a change in the sign of one of the couplings led to a bad mobility, right? Yeah. Did you understand that?
Yeah, okay. The point is that it was highly featured in the paper because we were surprised by it. But if you think about it, it's the same in band theory. So will not be surprised if you compute the effective mass and you change the sign, you get the same result. So less surprised. So one way of looking at it is that the transport is very coherent. There is no time in 1 picosecond to lose the coherence. Therefore, the charge will interact with itself as it moves, and therefore the sign of the interaction will create negative and positive interference. By the way, this is true for the hole. If you where the maximum mobility is when the product of the sign is positive. If you do electron, the product of the sign must be negative for the maximum mobility. So it's a matter of interference essentially and quantum effect, but not different than what you would see in band transport.
Okay. So thank you. I think it's a good moment to stop. Anyway, remember, we will have a question and answer sessions with this morning's speakers in 7 hours from now at 6 p.m. Central European Time. So thank you very much, Alessandro. Thank you, Christoph.
See you later, everybody.
And we are
goodbye also from my side.
Thank you. And we're going to meet again at 4 p.m. Central European Time with Annabella Selloni. So thank you very much. Thank you to the speakers and all to attendees, and see you later.
Yeah, see you later. Goodbye.